cuts off about the first 10 seconds of anything that uploads, so you typically don't get this little bit. And so this is going to be a continuation of, even though I know nobody's going to be watching because they're all arguing about Minecraft on the One Lone Coder Minecraft server. Anyway, I wanted to record the third section of this live stream series about how I go about making one of my videos for the YouTube channel. And we've been doing image processing, and we've looked at the videos called 8 Bits of Image Processing. If you've not seen the other 2 streams which talk about how we got this far, then you probably best go back and look at those. And tonight what we're going to do is tidy it all up. We've got sort of a basic infrastructure, we've done the 8 bits of image processing. It's now time to package it in such a way that the viewer can play with and interact with. So at the moment it still requires me to change the code to show the different algorithms. So I want to put a little bit of a user interface on it, and at the same time try and package it up, look at variable names, think about some of the comments and things like that that we need to put in the video before tomorrow, when I'm going to film the actual YouTube video and hopefully edit it as well. I've got a feeling this one, it's short enough that it won't take too long. That's going to be an interesting live stream setup, how to live stream me recording the YouTube video, because I need to use OBS to record the video, but I also need it to do the live stream. I'm going to have a think about that anyway. Oh, hey Progalt, how you doing? This is a continuation of the first 2 videos. The whole project is quite a selfish and potentially arrogant one. I just thought it might be interesting for me to have a record of how I go about doing my videos. Right, so where did we leave it last time? And as promised, I've not looked or changed any code in between these live streams, so it's all genuinely live. So it looks like we left it looking at a form of binary edge detect algorithm on this high contrast scene. And I remember we had a few issues with the camera settings sort of being a bit low and dim, but they seem to have sorted themselves out this time around, so that's good. I hope that works tomorrow as well. Right. So what I think we've got here on the screen, we've got input. Now all of the algorithms are going to require an input frame, so I'm going to label that, I think, and of course we'll have output as well. I don't think there's any need to show any more frames, but maybe here at the bottom of the screen we can start to display some user interface, because there's a variety of things the user might want to play with. Firstly, choosing different algorithms, and secondly, some of the algorithms have parameters that, as you change them, change the nature of the image processing. And even though it's a bit unusual to include a video with an 8 bits, one of my 8, sorry, start that again. Even though it's a bit unusual to include code with some of my 8 bits videos, I think this one is interesting enough that people might want to download it and play with it and see how it works for themselves. Hey, Twister. Right, so that being that, I'm not expecting a huge number of viewers tonight. As I've just mentioned, they're all currently arguing about Minecraft. So let's just refresh myself with the code that we got so far. So I had a couple of days off from this just because real life gets in the way. I can't work on everything every night. Working full time, got other One Lone Coder stuff to do, and always some in real life problems to deal with. So it's just when I get the opportunity. So we chose some 8 bits, and I think we actually chose 9, but it turned out that really convolution, blurring and sharpening, they're all sort of the same one. So I can pull that one out, and that gives us our 8 bits again. So I just want to update the list so I know what I'm doing one at a time. And we've got a frame width and height. We've described a frame. We've got a way of storing it. We created the basic pixel game engine, and we do some capturing from the camera. And we've got a whole bunch of intermediate variables. I don't know if we're even using some of those now, so we'll have to strip those back out. And it's basically split into 3 sections. The first is capturing the webcam image. The second is showing that particular algorithm doing what it's doing. And as you can see, most of it's commented out because we're only going to show one little bit of it at a time. And at the bottom, I'm drawing the input and output frames. And that's it. So that's quite nice. So I think there's now a little bit of housekeeping time. I'm going to start by doubling, or approximately doubling, the size of the screen vertically. Let's just see how that looks. Do I like bread? I noticed somebody kept leaving me some bread. So I'm thinking in this bottom area, I'm just going to have text displaying what a particular the inputs are, and they may change depending on the algorithm, but certainly for consistency we're going to have 1 to 8, and I'll tie those two keys 1 to 8 to choose the particular bit to look at. So let's start there. In fact, let's start by identifying input and output very simply. So once we've drawn the main camera, it's just a case of drawing in the correct location some labels. So I'll zoom in a little bit so it's easier to see the code. Draw text. Is draw text? No, it's draw string in Pixel Game Engine, isn't it? Draw string. So the frames were 240 high, and we were drawing them with a 10 pixel boundary at the top. So let's put a little pixel boundary at the bottom. So I probably wanted it 250, 255, something like that. And there were 320 in, plus 10, so we probably want it somewhere around the 150. So I'm hazarding a guess that this is probably where we want to place our string. And I'm simply going to call that one input. And we'll let it stay white. This is not meant to be particularly flashy. Let's just make sure I've got that in somewhat the right position. Hey, it looks like I know what I'm doing. Let's try that with output. Hey for wah 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 wah. Oh, and hey Fisk, and hey Ishi as well. This is part 3 of my video series where I'm live streaming the development of a video which I'm going to film tomorrow. So the next one over, of course, is going to be output. We know the height's going to be the same, so this one was 150. We know that there's another 320 plus 10, so potentially that's going to be somewhere around the 480 mark. I think that's going to be a bit too far to the right this time, but we'll have a look. You know what? I've been in this for a while. So let's put in the obvious ones now. Draw string. We'll go down the side, so 10, and we know that from 270 onwards, or because the pixels are 8 characters high, so about 270. Let's say 275. I'm going to put in some indicators of what we're doing. So bit 1 is going to be threshold. And we'll do that for each of the bits. Oh dear. Need a semicolon there. Do that for each of the bits, and we'll paste them out and label them accordingly. The idea is that when the user presses a particular key, we're going to show that algorithm. And I'll space all of these out by 10. I'm betting I'm going to run out of screen here thinking about this. 295, 305, 315, 325, 335, because I've got other things I want to display as well, so I don't want to run out of space. 345. And I can't remember the order of the bits, but now is the time probably to solidify that order. And this is where we need to do a bit of thinking. Oh, hey, Magetsu. We need to do a bit of thinking because I need to present the bits in an order that's quite sensible. Now, I do want to start with threshold because it's the simplest one. The second one, motion detection, that's equally simple too, and they're not related, so that's nice to just sort of ease us into what's going on. Then we started getting some of the more complicated ones, the spatial filters where we need to look at neighbours. So I might actually move this one, low-pass temporal filtering, to be in position 3. And that sounds horribly complicated, but it's a very simple one to implement, and is often necessary as a precursory step. So then we've got the odd one out here is median filter, because it doesn't really do. In fact, those two can probably be swapped around, because Sabel edge detection requires that you know what convolution is about. But these two at the end, now number 7 and 8, they're sort of standalone in a way. They do look at neighbour interactions, but they're not really relying on any of the techniques that we've looked at earlier. Yeah, we've been doing spatial temporal filters, Fisk. I know you've not really watched any of these streams, have you? They're on the Java X9 channel, but there's nothing in them that I don't think you're already familiar with. Right, so let's just make sure that the text is kind of in the right space and where I want it to be. Okay, so we've got lots of rooms. That's going to display which particular algorithms we're looking at any one time. So the first one was threshold. You know what, I'm just going to copy this list down there so I can see it. And we'll get rid of it in a minute. So the first one was threshold. Then we had motion. I'm just going to call it motion. It's not motion detection. It's just a motion map. In fact, let's be precise. It's absolute motion in this case. Then we're doing low-pass temporal filtering. Then it gets complicated because we've got erosion and dilation. Now, is it easier to do the convolution ones before erosion and dilation? It probably is, actually. So maybe that can go down here as a bit of an oddball one. Very useful techniques, but I'm starting to see a flow here where it becomes quite analog-y. The first one's very digital, but then it's sort of analog, 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 and then we're going into oddball ones. Okay, I think I'm happier with that order. I just, in the back of my head, I feel I can make the dialogue of the video flow a little easier. We need to make a Minecraft copy and host a server for it. Well, Gate Overvoltage, who are you on the Discord? Shout out, because there is now an official Minecraft server for the One Lone Coder Enterprises Megacorp. Definitely not just sucking all of your information low. Come on, David, spell properly. Right, what was next? So after low-pass temporal filtering, it was convolution. Now, that's going to be the first of one that has several options to it. Oh, I did this last time, didn't I? Convolution. Because we want to be able to change some of the kernels that's going on here, the blurring and the sharpening. So that'll sort of get split into two additional options. So after convolution, maybe I should put in brackets there. We'll look at blurring and sharpening, because there's loads of kernels, as we saw in part 2 of this series, but I don't really want to dig into loads of different types, because I really want each bit. I don't want to spend more than 3 or 4 minutes on in the video. 5, Sobel edge detection. Well, that's a classic. That's got to go in. Then 6 is erosion and dilation. I want to show those at the center. So that's probably the easiest way to do it, is to show erosion and dilation as separate entities, giving the user an option to choose between them. Let's call that what it should be: binary morphological operations. And we'll put in brackets erosion, dilation. Let's try and keep it consistent. So tonight's stream is about making the code into a final video code that I would normally upload to the video. So I start to think about it, look at the variable names, look at how the code is structured. We've done all of the sort of hardcore decision making on and getting the algorithms to work. Then finally we've got median filter, and we'll have adaptive threshold at the end, because that was a curious one. But do I want to end the video on something that's more entertaining? Because one of the things we didn't quite work out was how to demonstrate these two in an interesting way, in a way that's sort of immediately intuitive, as going, oh yeah, I can see why that's useful. They made lots of interesting patterns, but if you've only just started doing any image processing, you might not be completely aware of what's going on with those. But let's stick with that list for now. And we're going to want to change some of these things depending on what state we're currently in. So I'm going to not really use a state machine, but I'm going to create an enum that actually identifies which algorithm we're demonstrating at any one time. So I'll call that algorithm, and we know that we've got threshold. I'll type all these in again. I've forgotten what they are already. Try and get them in this order. What have we got? Let's just grab you and paste you up here again so I can see you. Whenever you do column select like I just did, always put in enough space to do the paste. Because sometimes it does horrible, nasty things. So if I paste in the middle of some code with a load of column select, see it merges it all together. So you want to avoid doing that if you can. And it does it. It's funny how Visual Studio does several things in one hit. So I'll just undo that, get rid of it there. So threshold. Then we've got motion. Then we've got low pass. Then we've got convolution. Then spell. Then morpho, lodge, or just call it morpho. Morpho's cool, isn't it? We need somebody with a username called morpho. Then we've got median filter and adaptive threshold. So we can put in median, and adaptive. So they're the 8 different things I'm going to show. Oh, hey, Lucas. Yeah, not bad, thank you. Right. I'm probably going to need that again at some point, but for now, what I'm going to do is split these into a case block to do the actual image processing. So I'll need a variable to keep track of what I'm doing. Algorithm. I'm just going to call that algo, and we'll default it to threshold. So, switch. I'll just have to do a bit of repetitive typing in here, get all of this sorted out. Let's see if I can use some Visual Studio foo to make this a bit easier. See, except unless it keeps moving things around like that. What I don't want are any of these commas at the end. That's confusing. What I do want is to select all of these and then do case, and then I don't know what the magic cursor commands are to paste things at the end of lines in columns. Ugh, just had loads of chili, I'm quite full. And then we want obviously some breaks to go with these. Now, a lot of people will know all the tricks to do this sort of thing really quickly. I quite like typing things sort of line by line because it slows me down enough to be thinking about what I want to do next. Because whilst I was doing that, I was thinking, well, I now need to, where am I going to put the user input on all of this? And I think the user input is probably going to go somewhere at the start here. So we're going to look for numbers for the main modes. So let's do that first. So if we can do this. Can do some Google foo. I mean, we're going to do some Visual Studio foo here. We've got 8 modes: 2, 3, 4, 5, 6, 7, 8. Okay. So if get key, OLC key. Let's just pick. Well, they're all going to be digits to start with. Oh, hang on, what are they? I think they're not numpad, I think they're K, and then the numeric equivalent for that. Dot be released, so only if the user has released the key, then we want to set what the algo should be. Algo equals, and then we'll put in a semicolon at the end. So I'll just whiz through these, 4, 5, 6, 7, 8. 2-dimensional coding, right? It's pretty cool. Algo equals, and then we need this list again. I don't think I've got a super quick way of. Oh, maybe I have actually got a super quick way. So I'm learning how to do these things faster. Ah, what's gone on there? Oh, it's done some. It's tried to be clever. Anyway, it's put things in the right place. That's not too bad, actually. There we go. Right, so that's going to respond to keyboard input and choose the appropriate algorithm, which will execute in our switch block. I think that's all okay so far. So let's just get on with it. I don't want to do individual functions for all of these because I just don't think it's necessary to have another layer of breakdown for what each particular thing we want to demonstrate is. So for threshold, we were just scrolling through all of the images. and outputting them. Now, the only time you have a problem doing sort of complex code in switch statements like this is if you're creating new variables. Sometimes it doesn't like that. But all we're doing for threshold is going through all of the pixels in the image and testing their value against this constant 0.5. Now, it's my intention later to make sure that these constants are modifiable so you can play with them in real time. So threshold was easy enough. Motion detection. Motion detection, very similar setup. So I'll also start looking at formatting this in a pleasing way. So motion detection, we went through all of the pixels and we compared the pixels this frame to the pixels in the previous frame, and we took the absolute value of them. Because we didn't come up with a way of rendering negative pixel values, we just discarded that information. But the negative, the sign bit of the pixel is actually a really useful bit of information because it can tell you about whether it's the new frame or the old frame that you're seeing. Very useful for determining, in a very low scale, you can determine direction. Then we went to temporal low pass filtering. Yeah, okay. So again, oh dear, I've put these things in. Now I was a little bit unhappy with some of the code for this. We might come back and tidy this one up a little bit better than we have here, but we'll see. So low pass filter, we went through all the pixels, we looked at the difference between the current input frame. Now this was the one that needed priming because it took a long time otherwise. Ocean detection, motion detection, again, this one has a constant in it which we probably want to be able to twiddle the value of, and we'll have to choose an appropriate minimum and maximum range for that. So that's telling me I need at least one twiddler somewhere in my GUI. I think I only need the one, and we can repurpose it for different algorithms. I'll have a think about that as we get to it. Convolution. Now, convolution was a bit of a tricky one because we had a lot of kernels set up, so we need to decide which kernel is going to be used for a given input. I'll tell you what, we'll come back to convolution later. Let's do some of the simpler ones first, because that's a multi-option one. So what wasn't a multi-option one? That's convolution, convolution. What was this one? This was... can't remember that one. I didn't put a comment on it. That's no good, is it? What's this one? This one was median filtering. I can tell because we're accumulating neighbor values and sorting them. So let's put in the median filter one. Have I gone past it already? There we go. What's going on, Visual Studio? I don't want that one. I want that one. Good enough. Median filter. Plop all that in there. So the median filter, just as a quick refresher, went through all of the pixels and looked at the surrounding area's neighbor pixels. So for every pixel you looked at, sort of, in this case it looks like we're doing a 5 by 5 matrix around that pixel. We're looking at it and we're taking those values, storing them all, and then we're sorting them. And we're going to take the one that's in the middle. In fact, it doesn't look like we're taking the one that's in the middle of a 5 by 5 kernel. So that's something interesting to look at. I guess that should probably be something like 12 now. So we've got a few algorithms in there already. We'll just... Yeah, for now I'll start to comment out pretty much everything except what we need up there. Because we'll come back to these. I just want to start testing things as we go now. But if I've got existing code in that space, it's not going to work very well. Right, I don't think I've got any existing code there, so let's just see if we've got, well, what happens at the moment then. Does it even compile? We might have a few things in the wrong place. So for 1, which is threshold, which is that, 2, which is motion, very nice. 3 was low pass filtering. Now that's behaving much better than it did last time, even without the primer. So that's filtering sort of very quick temporal noise that's going on. So you can see, I highlighted this in the previous video, you might not be able to see on the Twitch stream, but when you're running the code live, the webcam is inherently noisy, and those noise pixels can give you an issue if you're particularly trying to capture an image, and you can see the one on the right has basically no temporal noise on the pixels, but we've deliberately got a very high coefficient there, so that's why it looks ghostly and blurry. But that's quite nice. People can play with that. We've not got Sabel, but we have got median filter. Now this one was a little tricky to demonstrate. Oh, look at the performance tank there. What mode am I running in here? I'm actually running in release mode. We have to look at that. What we're doing for median filter there. There's a lot of computation happening. So the median filter we said was capable of. I've still got the test sheet that I used last time. That we can still keep the overall outline of a shape, but we can start to filter out the noise and crud that's in the background. And then we didn't fill any others, so I should just be able to switch between these. Whatever, I have to keep moving, switch between them, and good, that gives the user the ability to sort of sample them. Let's go and put in the other complicated ones. So adaptive threshold. Now this one again has a twiddly, so we'll need to. That's probably what yes, that's what this one was, wasn't it? God, that was a complicated sentence to say. So I'll take that. This was adaptive threshold, and we'll bang that in as well. As Visual Studio just literally vomits code wherever it feels like. Come on, there we go. Now this was for a 5x5 kernel, and I'll add comments in that describes what's going on here. But again, we go through all the pixels, we look at our immediate neighbours, and for the adaptive threshold, we're taking a sum of all of our region. Well, we take the average value of our regional neighbours, and then we threshold ourselves against some proportion of that average value. Now we'll see what this looks like, because I remember this was the one we started to have some difficulty visualizing, and again I think it's got a twiddly factor in it. So adaptive threshold number 8. Yeah, so this was the if you remember, this was shadow that this was a threshold that was shadow invariant. So if I bring my image on here, and it took a bit of a time to work out. So you can see I'm casting a shadow across the central high there. So I'm running out of sort of arm length to demonstrate this. But the threshold doesn't care. You don't sort of see it wildly change, and that's quite useful if you've got a strong light source in your scene that you're trying to analyze. So adaptive threshold, that one seems to be working. So it's just these tricky ones in the middle. I'm going to put them in. Let's get all the algorithms in first, and then we'll start adding the twiddlies. We'll come back to the morphological operations. Let's get into now how we're going to present the convolution. So there's 3 sub-options, well, 2 sub-options when we're doing convolution. So I probably need to display those as additional options the user can choose. So I have additional information I need to display on here depending on, again, which state are we in. So I'm going to switch on algo. So we know we've got, for convolution, a few of these actually probably have additional GUI properties we want to display. For convolution we want to do something, and for let's get all the ones that we need these for. So for threshold we actually want to be able to change the value of the threshold. Convolution we want to choose the convolution kernel. For low pass temporal filter we want to set the time constant. It's an RC constant, if anybody really knows what that means. If you were to, what it means is if you were to plot the particular function as an electrical schematic, you would represent its function as a resistor and capacitor linked together. Capacitor going from source to ground and the resistor in series with it to drain the capacitor. So here we've got convolution, and what were the others? We want the erosion. That's going to have a choice of 2. So morpho has got a choice of 2, hasn't it? Morpho has a choice, and adaptive threshold. We probably want to be able to tweak the parameter in that too. Adaptive. So these have all got unique GUI elements that we want to be, and if we've not got anything in there, default. Oh dear. Default. The trouble is, I can't touch type, right? That's to my shame, I can't touch type. I'm just going to stick a break in there for habit. And I can't see my keyboard because there's a giant microphone in the way, so that's why we get lots of typos when I'm live streaming. So let's just have a quick look at those, make sure I've not forgotten anything that's important. So the adaptive threshold, we've got median, there's nothing to set. Morpho, there is something set. Sibel, there's nothing to set. Convolution, we've got low pass, we've got motion, there's nothing to set. And threshold, there is something to set. So the idea is now when we're in one of those modes, I want to display additional instructions under the algorithm. My grandmother was a teacher, and she used to teach typing on typewriters to, at the time, secretaries and things like that. And so she had a teaching typewriter at her house, and it had a big box that you would fold over the typewriter with your hands going through a little letterbox in the front, so the students couldn't see the keys they were meant to be pressing. So it was a really brutal way of forcing students to learn how to type quickly back in the day when that was a necessary thing for ladies to go and train how to be secretaries and things like that. Possibly they reached 120 words per minute. I'm certainly nothing like that. So let's start storing some of these constants as useful variable names, so people looking at the code can understand what's going on. So that's the algorithm that's currently running. So let's see algo. So I have to sort of look around. That's what I'm at the keyboard. Algorithm currently running. Right, so for threshold, we want a threshold value. So we'll put in f threshold value, and by default we'll have that at 0.5. See, there's one of these algorithms where we wanted to also change the number of iterations of something. So the threshold value is at 0.5 for that. So let's do that one first. I also probably want then in my algorithm switch here, we probably want to do a bit of getting the user input in order to get that threshold value. So this 0.5 is now f threshold value. And the keys I'm going to use are, I'll use Q and W or Z and X. Z and X, I think, to change the value. Or up and down? Up and down? No, Z and X. It's easier to display Z and X, I think. Yeah, I used to be great with my thumbs on a Nokia 5110. You could bash out text messages in seconds, not even looking at the screen. I can't do that now. I did actually try recently on the new 3110 to try and type in a text message, but it was a real mess. Right, so if get key OLC key Z, if that's held, then we're going to decrease our threshold value. Threshold value minus equals, I don't know, some constant we want to change it. So if I'm going to modulate it with f elapsed time. So if we're saying that on the whole it'll take 10 seconds to go from one value to the other, so that's 0.1 times f elapsed time. And we'll do the same in the opposite direction with x, so that'll increase the threshold value. And I need to clamp those to make sure, well, it stays within range. If the standard clamp function, I believe, is part of the next round of C++ versions. It's not here yet. It should be. So if f threshold value is greater than 1, then f threshold value equals 1. And likewise, something for 0. It's less than 0. So that little bit of user interface code is going to allow us to set the threshold value. Now I want to also display that threshold value and some instructions on how to use it. So when we're in threshold mode, I'm going to draw string. Now let's try and get this in the right place. I think we're not going to clash with that particular line, but I'm probably safe to start at 340 as a boundary, I think. So let's try 340, and we started this list at 275, so I'm going to start the next one at 285. And it'll be change threshold with Z and X keys. Change threshold value with Z and X keys. Let's get rid of the T there. Let's just see if that's in roughly the right place before we get too carried away with this. You see, so I'm a little bit too far over there, and I've actually got space down here to put it, so maybe I'll just add it to the bottom of this list. But let's just see if it works. So we're in threshold mode, so I'm holding down Z and the threshold is lowering, so we're seeing more white pixels. I'm holding down X and the threshold is raising, so eventually we lose everything until it's 1. Yeah, okay. Maybe I should also display what the current threshold value is too. So I'm going to change this to being sort of further on in our vertical list, so 10, and we'll start at 375. Vertically down, and we'll have draw string underneath that, so 10, 385, current value equals, and we'll just append to that to string f threshold value. Quick run, see if it works. So threshold 0.5 and should clamp out at 1, and it should take us 10 seconds to get from one to the other. I think you can kind of see that it does. So if I go the other way, it just counts down in seconds, and that was the 0.1 modulated with f elapsed time, controlling that speed for us. That's interesting. So we're getting some values there. That's because I noticed in the threshold code actually we have a little bug in our threshold. It's the simplest one, but I think it's a little bug. Is it? Yes. We're only looking to see if it exceeds the threshold value. We're not looking to see if it is equal to the threshold value. And so some pixels will genuinely be 0. At least I hope that's the case. We'll find out now. Yoink. Yeah, there we go. All gone. Okay, so that's nice. And I think that one's done. I guess the only thing I've not got is actually what is the current algorithm being executed. So should I display that as well? Possibly. Maybe we'll worry about that later on. Let's carry on with the more functional code. So threshold value, respond to user input in that case, and perform threshold per pixel. Good. Have a quick look at the chat. You should try making a filter that guesses the depth of the image. It's not entirely impossible. If I had a way of, and I do with this webcam, but I can't have it exposed in this interface. If I had a way of changing the focus of the camera, then yes, I could probably do it, because I could work out using the convolution technique regions which are in focus and which aren't. And as a consequence, I could then sweep through the focal range of the camera, taking an image at all of these different focuses, and from that I could reconstruct a really coarse and noisy depth map. So it is kind of possible, but it requires a bit of mechanical intervention. And without any prior knowledge or priming, I don't think there is any way, in fact I'm reasonably convinced, there is no way to extract depth information from a single image unless it's been primed with, well, this is potentially some table and this is potentially an object that's on the table. So that's at a different level of algorithm entirely. Someone ever used OpenGL with the console game engine? Probably not. Right, motion. There's actually nothing to do with motion, but I will write in a description of what it is motion does. Motion returns the difference between successive frames. In fact, it returns the absolute difference between successive frames per pixel. Motion's okay. Lowpass, so that's the next one with a twiddly. And we can probably use a lot of the twiddly stuff that we've already got. We can cut and paste our way out of this one, but we'll see. So float, for this one we'll have Lowpass. I'm going to call it Lowpass RC, and it's defaulted at the moment to 0.1. Now, this one will need to be clamped slightly differently because, excuse me, if we went to some really low values, you'll never see anything happen. So I need to kind of keep it within an interesting bound. So we'll just take those and we'll stick that into Lowpass. Change RC constant. Tau is the word. If anybody knows what... I've not got a tau character anyway, so I'll not display that with the Z next keys. So current value equals that, and it was Lowpass RC was the variable that we're changing. And I need to go up here to where I'm handling user input, which is per operation. I'll just grab the same sort of thing for Lowpass. So it's Z and this, yeah, Lowpass RC. So if I leave it right now at being the same, oh, and I'll just also change this constant here to the twiddly. If I leave it like this, I just don't think we're going to see a very interesting effect, because I think it'll very quickly become totally unusable. So 1, 2 is absolute motion, 3 low pass temporal filtering. So I've got to wave my arm around here. So it's currently set at 0.1. If I make that larger and larger and larger, what we'll see how the image is now more live. There's a lot less ghosting, but at the same time we see a lot more background noise. But if I go lower and lower and lower, I get ghostier and ghostier and ghostier until essentially the image will stop. In fact, at 0, of course, the image will stop entirely because there's nothing there to update it. So here, this is why it's called low pass filtering, because I've brought my hand into the scene and we're currently seeing it's taking quite a duration in this case for my hand to appear. So it's a way of, you can also use this approach for background learning. So let's say I have the camera constantly pointing at a scene. I can then use that as a background in an image where something moves across. So something has moved across, it's barely changed the background image. So I can use that as a subtraction mechanism to actually extract whatever has moved across the scene from the image. I think we tried that last time, but I didn't code it very well, and that's why we didn't see the result that I expected. So I could move all of that motion that's just happened on the left, I could just subtract the background image to highlight that motion in an interesting way, perhaps. But if I increase the time constant, that's a little bit more interesting to look at. Nice. And I've got the text is right. Change RC constant value with next use. So do I need to change the bounds there? Because once you get to sort of anywhere near 0.5, I guess no, there's still some visibility there. But you get to a point where it stops being silly. And I think if we actually saturate that at 1, I think even before that. Oh no, there's still a bit there. No, I'm going to leave it between 0 and 1 then, but the sweet spot for interesting stuff is around 0.1, 0.2, something like that. Let me just catch up with the chat because we've got a few things being put in. I have a question. I program hobby projects and in C++ and school projects in MATLAB, but want to get used to C# for the sake of it. I was thinking the approach of using dnspy to decompile Unity game DLLs back into C# to modify the classes, etc., to learn how the syntax works from trial and error. But this may not be the most elegant way to learn, but I don't have much time to spend learning another language. That sounds, frankly, and don't take this the wrong way, that sounds like the absolute worst way to learn how to program anything. To take some code and then decompile it. It's just not going to really tell you anything useful. It'll just be code. And it'll be the decompiler's interpretation of the code as well, not the programmer. So I have to say I really wouldn't recommend that as being a useful way to learn how to code. If you are good with C++, anyway, as Humper Lumper has mentioned, moving to C# is probably not going to be a big challenge for you. But yes, anything, as others have pointed out, anything that involves decompiling code, it's not going to look like the code that I'm writing now. I know that recently there's been this new, and I'm sure somebody will put in the chat this new name of whatever is it the NSA or somebody have just released a decompiling package, and it's interesting to see the code that it produces. But again, it doesn't know what the variable names are. It doesn't know things like class names or anything like that. So you'd still have to go through it and work out what the code is doing in a semantic way. And that you may as well just, if you've got an idea for something, you may as well just code it yourself. It'll be a bit quicker. Well, C# code probably can decompile pretty well because it's not compiled in the same way as say C++ code for x86 machines. I'm not a C# programmer, but I'm reasonably sure it compiles to a virtual machine-like bytecode, which is probably a lot easier to reassemble because the virtual machine can have all sorts of funky and interesting instructions which normal processors don't have. Right, where were we up to? Right, we're up to adding more stuff in. So a little diversion there. Convolutions. Oh, we'll just put in some comments here. So we've done low-pass filtering, and we are looking at commenting. That's what I'm doing. So we're going to go through each of the pixel and run it through a RC filter. A temporal RC filter is a bit of an overstatement. Of course, it's RC, it implies that it's temporal, but I think things like this help people just realise, hang on, this is an operation in time. Might also be worth sticking a Wikipedia link to an RC filter and what it is. Right, next one with some interaction. On my list, convolution will come back to adaptive. So adaptive is pretty much the same as this threshold, it's just specifying this biasing value. Change adaptive threshold. Well, you know what, yeah, okay, I'll call it adaptive, adap adaptive threshold. It's not a value this time, it's a bias. We'll have to have a think about how that is implemented. So f adaptive bias. I've not got a variable for that, need to create one, which will be stuck up here. I think at the moment, if I recall, we've got it set to 1.1 as a default. What I'll do is I'll clamp that to a range between, say, 0.8 or 0.5 and 1.5, say. So let's go in and copy and paste again our threshold. Low pass, adaptive, so we'll do a bit of user input in here. F adaptive bias. But I do want to change some of these values. If it's greater than 1.5, wasn't it? That's what I said. And if it's less than 0.5, 0.5 and 1.5. Then we go through it pixel by pixel over a 5 by 5 adaptive regional kernel. It's not quite a kernel in this sense though, and that was our twiddle value. F adaptive bias. And this is one of the reasons I like the pixel game engine and I like the console game engine, is there's really no effort in just putting these little experiments together. So let's go to adaptive threshold, and we've got a bias. So if I lower that bias, we start to see, things start to look quite cool. Perhaps you want to use this as a pencil drawing effect, perhaps, who knows. Again, it's shadow invariant, and that's the cool thing. So you might want something like that as a precursor to a cell shading algorithm, or I don't know. And to the other extreme, if we bias it completely the other way, the image will start to collapse if you over bias, like it has done just here. So it becomes meaningless. Okay, yeah, that's it, that's good enough. I'm still going to have to think about a suitable demonstration piece for that. Let's have a quick look at the chats. I don't know, they're arguing about something, but at least they're not arguing about Minecraft. Right. So, next we've got Convolution, Sibel, and Morpho, the ones we've not implemented, and I think they're also ones with, well, Convolution and Morpho are. So let's think about how we're going to store these kernels and how we're going to switch between them. The kernels never change, and for this approach, I don't think I want to allow the user to change the kernels in real time. Somebody else can go and modify that in. I don't think it's necessary to prove the point I'm trying to prove. So let's add in a bit more information that we need. So have these hard-coded kernels in. And I will make them look a little prettier by trying to just align them up so people can see it's basically a 3 by 3 matrix of numbers. What kernel is that? That to me looks like a blurring kernel. So I will put in kernel blur and give it a name. The next one, did I only copy one over? Oh no, sharpening kernel, I didn't, yeah. So that's a blurring kernel. The next one is a sharpening kernel. And I remember in the last video we demonstrated that by changing this middle value you can start to change the nature of what the convolution is doing. And what was it we were doing? We were looking between doing sharpening versus blurring and something else. I think it was like edge detect started to come into it as we changed the middle value. So that was for kernel for sharpen. Put that in, and they're nicely spaced out. You know what? I'm just going to add in an additional space there, just so it's clear. Yeah. Even though they're not all the same, I quite like the look of how that looks. So that's why we got an error up here. Kernel blur. incomplete type not allowed. What have we missed out? I think that's just some Visual Studio leftover from IntelliSense not ticking over. Oh no, this is actually an error. Array bound cannot be deduced from. Oh, I can't do this in the class header, can I? That's frustrating. I wonder, can I actually initialize them like this? Well, it didn't complain at me. So that's kernel blur, and we had some other kernels as well, didn't we? We had the Sibel kernel. So whilst I'm working with kernels, I'll just pull those out as well. Let's just take the comments off them. There's a bit of code sculpting tonight, so we'll try and stay with a reasonable naming convention. Kernel Sibel horizontal and kernel Sibel vertical. And people are going to shout at me with the Sibel part because I'm not sticking truly to the Sibel. I'm not doing the square root because I don't think you need to. Right, so now we need to implement the convolution, choosing a particular kernel. So I need some sort of way of referencing those hard-coded kernels that we've created. So I will throw in an additional variable, which is indeed a pointer to a particular kernel. So in this case, it's going to be f p convo kernel. I don't think I can do what I'm about to do, but we'll see. By default, we'll have it to kernel blur. I don't think it's going to like that at all. Oh, have I missed off some numbers somewhere? Yeah, missed a number. Okay, well it compiles and it's run, but I don't know if those values have been set up properly, but we'll see. So pconvo kernel has been defaulted to the kernel for blur. The Sibel ones, they're going to be hard-coded in, but we're going to have some repetition with the convolution code. So maybe it is time to throw in a lambda function or something like that to actually just do the convolution again. Anyway, let's start by just getting the convolution code in. We were running multiple iterations of the convolution code. I'm not going to show that in this algorithm, I think, mainly because it will start to cripple the frame rate. You wouldn't want to do convolution over a large area by rerunning convolution over a small area multiple times. Even though the output is quite interesting, I just think it's a step too far for a video where I've got to try and describe this topic in just a handful of minutes. Right, what have we got? So we were using activity equals output. Why were we using a different? This is Sibel. I put that in the wrong place. Okay, let's do Sibel then, since I've got the code right here. Even though, I mean, convolution is convolution. But since Sibel is on my doorstep, let's do that. Activity equals output. It's because we were looping through it a number of iterations, wasn't it? Which we never need to do for Sibel, so that makes no sense. Mouse is very snappy today. Alright, so what are we doing? We're going through each of the frames and then we're basically convolving the same frame twice, but with two different values. We're only looking at the inputs and writing to the outputs, but we'll see, we've got this activity value here. So kernel sum equals in activity. Let's just change that to input. And that to input. We look at our neighbor values and now we can go straight to kernel Sibel H. Oh, so I already got the Sibel and V there. Kernel, Sibel and V. And we add up our two sums, and you're supposed to do some interesting thing with square root here, but I don't. All I do, because they try and do it mathematically. So the idea is you want to get rid of the negative values. Now, why did we offset this to 0.5? Were we looking at... I think we were looking at the direction, weren't we, of the Sibel? Now, is that a different option that we want to include? Let me just see if this works. Refresh my memory with what we're doing here. So if I pull in the Sibel, which is number 5, yeah, that's what we were looking at, wasn't it? We were looking at primitive sort of edge labeling. So horizontal edges getting labeled. Let me pull up a more high contrast image I've got control of. Where is my little test thing? There it is. So what we were looking at in this case is, we were making it, that was it, we were making sort of an artificial bump map creation algorithm using Sibel. So that's where the code was left over. So hang on, let me catch up with the chat. There's a question that's happened. Hi, is there any reason you prefix the 2 with the sign in the for loops 2, 4, 8 and 2, 4, 9? With the plus sign. Let's quickly run the code. Yeah, it's a visual aid. Other than it for me it demonstrates. Hang on, you are going from negative through 0 to positive. The plus does nothing functionally to change the code here, other than it tells me that I'm switching domains. It's unusual to see a plus there. Why is there a plus there? And it's because I'm not iterating from 1 to 2. I'm iterating through 0. So I just find that as a nice little way to keep track of the code. Remember, I want to make my code as fluent to read as I can. At the moment, it still isn't. There's still some work to do. But when I'm reading code, I like to be able to read it at the speed, say, a musician can read sheet music. You just want to go quickly. Yeah, okay, we're iterating over something here with negative offsets. I know why, because we've got a kernel going on. Fine, that makes sense. That means we're centralizing around a pixel. It just makes things flow a little better for me. But this isn't Sibel as an output. This is this artificial bump map that we created, because people were interested. How can I take a 2D image and create some sort of fake luminance for it? And that's what we did. But we're going to get rid of all of that now, even though it looks very pretty, because it's not actually Sibel. So for my Sibel, we were just going to divide by 2, get rid of the offset, and we were taking the absolute value of all of that. Why don't you use polymorphism? You explained it a few videos ago, and this would be a nice use case. Yes, it would be a nice use case. It's probably too simple, is the answer. Because I don't like unnecessarily going down the object-oriented programming route. I think a lot of students now at university are taught that you've got to do things with as much encapsulation as possible and try and make the code as clever and interesting as possible, and he just doesn't need it. I've got 8 algorithms here. They're broadly similar, so yes, they do classify for polymorphism, but I just don't really need to create unique classes for them all, and I'm just, some of these algorithms are 3 lines of code long. For me to go and create the classes, it's more code and more files and things. But also, don't lose focus of what this is about. This is part 3 in a series of me recording how I go about creating the video code. And this video is going to be 8 bits of image processing you should know. So I'm going to actually spend very little time talking about the code and more time talking about the image processing. So I just want the algorithms to be visible up front and center with what they are. So it's really just, I just don't want to overcomplicate it. And I don't mind files. With some of my work files, some of the programs in there, they have over 5,000 or 6,000 lines, and that's fine. I don't have a problem with that. No, this one, when it's finished, when we get rid of all of this commented stuff, this one's only going to be about 500 lines long, and we've got 8 different image processing algorithms in there, all visually displayed and user configurable in 500 lines of code. So Sibel, that's what we were testing. We took out the artificial bump mapping. So this should be a more genuine Sibel. Oh no, it's not. Oh, hang on, we need to actually choose Sibel, don't we? There we go, that looks a bit more like Sibel that everybody knows and loves. So that's just a general purpose edge detect, and the absolute in space of the square root symbol has done the sign removal for us. Well, thank you for that. So yeah, Sibel. Sibel is done. There's nothing we can twiddle on Sibel. No, there is nothing we can twiddle on Sibel. So there's no user input required for that. I'll come up with some comment for it later. So now we've got what have we got left? The two big ones, Convolution, which we've kind of just done for the Sibel. So let's do that one first. I don't think I've actually got convolution code on its own, because in the last video I just modified the Sibel one, didn't I? Yeah. So I'll just do exactly the same, but reverse the process. So I'll take Sibel, and for convolution, we're going through each frame. We don't need that. We do need a sum. Our kernels are all 3 by 3, and our sum value is going to be that, and the kernel is the thing that we're going to switch between, isn't it? And all we're setting for the output is the... Technically, we actually do want to just set the sum value for convolution, so let's start with that. Because the kernel should be normalized, so on average you get a value that's within your pixel range. But we'll see. We'll see what happens. Fsum. Get rid of that bracket. But we need to now use our pconvo kernel. Yes, pconvo kernel pointer to select the blur. It was blurring, wasn't it, the first one? So let's just make sure that that code makes sense. And then we'll add in the user input to choose between the two kernels and update what's displayed on the screen. So it's number 4 this time, convolution. And you can see it has ever so slightly blurred the image. Now this is why we wanted to run it multiple iterations, because it's not that easy to see on this screen. I mean, it has done. I can see quite clearly that it has applied a very slight blur to the image. Anybody that does image processing properly would never do convolution this way unless they really had to. This is a way that's easy to describe what the mechanism is and show what the results are. If you're serious about doing convolution, you really should be doing it in the frequency domain. So you would take a 2D fast Fourier transform of your source image, and you'd take a 2D fast Fourier transform of your kernel, and you simply, I can't remember which one it is, but you simply add them together, and that's it. And then when you do an inverse 2D fast Fourier transform of the result, it's done exactly the code that we've done here. Now that might sound horrible. Why are we doing all of these fast Fourier transforms? It's going to be terrible. Well, right now we're limited to kernels of small dimensions, so we've got a 3 by 3 kernel happening here, and we tried 5 by 5 as well before. But if you wanted a 30 by 30 kernel, the sheer number of computations that need to occur in order to make that happen will cripple your system. But in the Fourier domain, you know the length it takes, you know the amount of cycles it takes to do the fast Fourier transforms, they remain fixed. And then adding them together, that remains fixed. So you can start doing very large and complicated kernels with no additional performance overhead. Anyway, that's a trap for new players, is it? That's what they say, trap for young guys. Not quite, Fisk. When I did the soft shadows, I used a technique called linear separable Gaussians, combined with another trick that I've shown in here. And that's I think that's worthy of a video in its own right, but it would be quite maths heavy, as would this one here has been, this FFT. Oh, hey DW. And the nice thing about linear separable Gaussians is you can treat your 2D array as being a set of rows and a set of columns. So most blurring algorithms, you need to consider space in 2 dimensions, and that's why they become computationally complex. Not very good for your CPU. You've got to go through the pixels, as we're doing here, and mess up your cache. There's no nice way to optimize it. But if you could represent your image as basically a single line, a long line, take every single row and stack them all up next to each other in one big line, and pass it through a standard set of taps in your filter, then it actually works, because Gaussians are nice and uniform in all radial directions. So you would first of all do it across all of the rows, and then you do it across all of the columns, up and down and left and right, and it works, and it's very nice and easy to parallelize, and that's why I could get it running quite quickly. You can also do interesting things with separable Gaussian blurring, that you don't have to do radial symmetrical Gaussians instead. You can actually use rotated, elongated Gaussians, so Gaussians with non-standard aspect ratios. And this can open up all sorts of interesting things to do with neural networks, and maybe we'll talk about that at some point in the future, but I think we're getting well beyond what I'm trying to demonstrate in this video. But one of the nice things about doing Gaussian blurs quickly is you can do Laplacian transforms, and that's a big deal. If you want to do some really funky on-screen effects and algorithms, Laplacian transforms are really quite an interesting thing, and I definitely want to do something on those. Hey Plexum. What on earth is a Gaussian? Oh dear me. Yeah. Danicon, a way to create a blurry image. Yes, it is. If you're using it in the context of image processing, you can do a blur with a Gaussian. What is the mathematical definition of a Gaussian? It's a curve where its derivative is always its derivative, or something horrible like that. You can tell it's too late on a Friday afternoon. And I'm in my funeral shirt, of all things. Not had a good day today. So that's why I'm not going to go into what is a Gaussian. And that's why I'm not including it in my 8 bits of image processing, because you do have to then start explaining what are Gaussians. And if you saw a Gaussian curve, you'll recognize it straight away. Funnily enough, whilst we're talking about blurring, we're doing a blurring kernel here. Kernel blur. This, you could go away and calculate the Gaussian components for your blur location coefficients, but I'm not doing that. I mean, I hacked this one together in my head. It's roughly a binomial distribution, so it's not a true Gaussian, and that could give you some interesting artifacts if you use slightly larger kernels. You'll start seeing blurring, but it will have ever so slight squariness to it, but only over extreme blurs. Right, what was next? So we wanted to put in a selector to choose between which kernel we're currently showing on the image. So I need to put some user input in, don't I? And this one's now a bit different, because we're selecting between 2 different kernels. Right, I'm up to speed with what it is I'm doing. At least one of us is. So I don't think I need the clamping for this, because there's no numerical thing being changed. So I'll stay with the Z and X keys. So if they press the Z key, our pconvo kernel, I'm going to set that to be the address of our kernel blur. So that just keeps it as it is. But if it's X, copy. If it's X, I want to set that to be our kernel sharpen. So if I keep looking down, it's because my chat's here in the corner. So I've got the 2 convolution kernels. I then need to display which one I'm currently using. So we've got some information down here. We'll do the same sort of thing. Change convolution kernel with Z and X keys. with Z and X keys, current kernel, and I'm going to upset people by using the ternary operator, but you know what? Go away. It's going to be a choice of blur. Actually need to put in the condition first, don't I? P convo kernel equals kernel blur, then return blur, else, well, I've only got the 2 in this demonstration, so then it'll be sharpen. It does all of that. Need another bracket. Expression must have integral or unscoped enum type. Where? Oh, hang on. It's something stupid like that. Now, what's going on here? Why won't it let me append the string from this result? Convolution kernel equals blur. If that's the case, return blur. Come on, guys, help me out. What are we going on here? Why can't I just append the result of this ternary operator? Expression must have integral or unscoped enum type. Brackets all seem sensible. Do you need to call the standard string constructor? Well, I was hoping it would be a little bit more smart than that. Yeah. I thought it would pick up on that because there's it's clearly obvious what the return type of that ternary is. Well, maybe it isn't. Maybe it thinks, oh, I'm actually, yes, it's classifying that as a const char there. So fair enough. Okay, it was thinking I was trying to add a numeric to this string. Okay, compiler 1, Javid nil. Fair enough. So chosen the particular convolution kernel I am looking at. Hey, Tezza. And it will choose one or the other. So let's just see if this works. Oh, I've got horrible pointer errors and memory errors all over the place. See what happens. So we'll go into convolution mode, which is 4. So by default it's blurring. We change to 1, and it's sharpening. So blurring, sharpening, blurring, sharpening. Pull in my test sample. Blurring, sharpening. I think the sharpen looks a little bit aggressive. Is that because I left one of the values to be unbalanced, or did we decide it needed to be overbalanced? I think we did, didn't we? So if we made all of these equal each other, which is what potentially maybe you want to do, the downside here is that the resultant sum of the kernel is 0. Let's go into thingy mode and sharpen. So yeah, you end up with an edge detect instead. Although a particularly awkward edge detect, because rather than detecting the lines, it's detecting the edges between the lines. It's like an internal edge detect on that one. I think there are better digital edge detects. The nice thing I like about the sharpen algorithm, though, is it shows all the noise coming in through the MPEG compression from the webcam. You can't see them there, but here I can see little individual squares, like a JPEG image getting corrupted. I'm going to put that back because I think you want some of the original content in, which is why we bias the middle pixel with what its neighbours are doing. So we've chosen the 2 convolution kernels now. Just want to make sure I'm not running on too long for the stream. But I did want to get this wrapped up tonight, really. So we're left with finally now with the morphological operations. Hack to scale luminance. Well, I don't need to do that today because the camera is behaving. So tell you what, I can just get rid of all of that. I'm going to start lopping out some code now. And I've done convolutions, so that can all go. I'm not going to do multiple convolutions on a single image. I don't think it buys us anything other than showing you can make something blurrier. We've done, that was adaptive threshold, that can go. We've done median filter, that can go. So the last one was this slightly more tricky one to describe, which was erosion and dilation. So let's do that, and that required a third. Excuse me. That required a third register. Register? Frame. Well, I'm definitely dipping back into my university days then. We used to call the images registers because I had processors which we'd designed where the individual processor registers held entire images. If we can get rid of... I think we needed threshold to start this one off, didn't we? Well, there we go, yeah, so we were thresholding it there. So let's just take this code and then start hacking it together. But erosion and dilation, even though I've bundled them into the same bit, they're actually two quite different algorithms in a way. But maybe there's a way I can bluff it into being a little bit more consistent, so I don't have to duplicate too much code. Let's see anyway. So the first thing we want to do for any of these things is we need the thresholded image because we're operating on binarized images. Let's have a quick glance at some of the chats. I seem to be missing a fair few now. Somebody mentioned JavaScript in my chat. Be careful. Next step in your syntax is to hold down Control and press the different effects to combine them. Too many coders and too many languages here. Good. It's just general chit chat. I'm not missing too much. That's good. So why were we doing this? Let me just think what we were doing here. So for dilation, first thing I wanted to do was binarize the image. So this one was useful. It was a bit tricky, sorry, not useful, because we wanted to display the input image, but then you want to display the thresholded image and see what the result of the thresholded image is. So I think we might need, just for this one, a slightly different approach to rendering the frames. We'll take it one step at a time though. So the first thing we're doing is binarizing the image. And we may want to do multiple numbers of these as well. So there's quite a lot going on in this setup. So the thresholded output, that's what we were doing. So we were setting that temporary thresholded image to activity. Then we wanted to do a number of erosions or dilations. Just uncomment all of that. And I think I need to bring it back a tab. So dilation was taking the thresholded image, and for every white pixel, if you're a white pixel and you exist, expand outwards, make your neighbours white as well. So that was easy enough. But I want to display things a bit differently here, and we need to have that count. Okay, so when we're in morpho mode, we need to do things a bit differently at the bottom. So that's here. If algo equals morpho, well, if it's not equal morpho, we want to do what we normally do. Otherwise, I want to display things a bit different. So instead of displaying input and output, I'm displaying, I believe, if I recall, it's threshold and well, it's threshold and output. Yeah. Okay. I could probably tidy that up as well. We're only switching one thing at a time, so I could probably do something like that instead. Okay, let's just see what happens with this. I can't remember what state we left it in because I think I tried 4-way connectivity and 8-way connectivity for this operation. What have we got? So this is 6, number 6. So we've got the threshold image and its dilated counterpart with a single round of dilations by the looks of it. Right, so I'm going to use the same threshold that we used before, so I need to change that value over. So they can go and set up the threshold beforehand. Sabel, Morpho. There we go. So this 0.2 F threshold value. So we'll use the same that you see in the threshold image. That way you can set it up with the camera beforehand and it gets carried over. And then we want to do a round of dilations. Okay, dilation's a bit of an interesting one. I wonder if it's worth splitting these up even further, because I think there's 3 interesting parts to show with morphological operations, and perhaps they're subcategories. Do you know what? I'll throw in another enum just for the morpho ones. Morphops. Morphop. And what do I want? I want dilation, erosion, and the third one's a bit of a bonus one, edge. So it's sort of a binary way of extracting the edge information in a really nice way too. People quite liked that algorithm, so I want to show it. And our default morphop is going to be dilation, and we need another value. Another value to how many iterations of these do we want. So int n morph count. By default I'll set that at 1. So a few things to get our head around here before we start running some code. Always we want the threshold. Now we want to do different things. So if switch morph case dilation, which is what we've got, do all of that. So we'll just stick another break in here. And pop you forward a tab. Don't need that comment, a bit redundant. So that's doing dilation, and then we wanted one for erosion. See, this is the bit that I think is going to take the most time to talk about. And then there was case edge, which was the same as erosion but with a different condition. So dilation is fine. Let's get rid of some of these other junk ones that we're not using anymore. Showing threshold, motion detection can go, low pass filtering can go. Erosion is this was an interesting one, wasn't it? So we've got that's all we've got left. Left is erosion. That's nice. Copy. So for erosion, we've got the thresholded image already. Then we're going to go through each of the pixels and we're going to look at all of its neighbors in this instance, which was 8-way connectivity, and only in this condition of a pixel being white. I think that's set up for the edge detect, but we'll have a look. So I need a way now of specifying. Hello? Oh, great! I've missed a squiggly somewhere. one's okay. That one's okay. I think there's an error in a squiggly. Adaptive. Where's my squiggly lines running out? There. It's the original. It's this morpho case, isn't it? Yeah, I've not put that one in. So case erosion, case edge. It's there. Yeah. Good. So dilation, erosion, we now need a way to select between these things. So we need to do a bit of user input again. So where have I got user input? There we go. Respond to user input. And at this time we'll use the Z, X and C key because we've got 3 options to choose from. So if Z is held, then the morpho is going to be dilate. It wasn't morpho, was it? It was just morph. Or it's going to be... Did I call it dilation? I did. I called it dilation. Dilation. Ugh. Or erosion. And the third one, edge. We'll stick in as a C, and at the bottom I want to display which one it actually is. And I'm not going to use a ternary for this one because I think it would start to look a little bit clumsy because I'd need sort of nested ternaries in order to get what I want. So it's just simply, we'll just do it the old school way. If morph equals dilation, do that. Current operation equals dilation. Fat finger syndrome, that's what I'm suffering from. And edge, and so this time it's change operation with Z, X and C keys. Now there's also going to be an additional up and down parameter in this because we want to change the number of iterations. So, but we'll come back to that in a minute. Let's just see if we've got anything kind of working now, because edge, I think we may have got these the wrong way around, but we'll have a look. Let's just see what we get. So here we've got number 6, which is the one I'm working on. So that's a dilation with Z. X, yep, so X is giving me single pixel edges for things, so that's what we wanted for the other one. So yeah, I've got edge and erosion mixed up. Fair enough. I'll just cut and paste that out because they're actually exactly the same code. The only difference is for edge it's equals, and for erosion it's less than or equals, I think. What are we on? Number 6 and X. No, it's not less than or equals, it's just less than. Now that's doing 3 iterations of erosion, so that might also be a bit of a problem for us. Six and X. Yeah, okay. Makes a bit more sense. So erosion and dilation, in a way, are the same thing. So if I pop that back into dilation, what we see in dilation is any white pixel in the input image gets expanded, and effectively in erosion, any black pixel in the input image gets expanded. So you could do this by first inverting the image and doing a dilation. So one man's dilation is another man's erosion. These algorithms are also called opening and closing in this space as well. And why are they useful? Let's just have a look at edge. Everybody likes edge because it's a really nice edge. that you get from it. Why are they useful? Well, they clean up noise, fundamentally, noise around the edges of things. So if I dilate and erode a certain number of times, I can start to remove awkward edge features and individual pixels. And that's why it's important to be able to have a varying number of iterations and dilations too. This one might be a bit too difficult to describe as a single bit. So we should have now all of the algorithms. So threshold, absolute motion, low pass temporal filtering. There we go, low pass temporal filtering. Convolution with blurring and sharpening. Number 5 is Sabel edge detection. Number 6 we've got edge in sort of morphological space. Output there is set to erosion and dilation. So that's quite an interesting one. When we got the light balanced right there, if I can just take out some of the auto exposure, look at the word high on the side of the screen. If I can find the right place for this again. The truth, in an ideal world, if you're doing image processing, the first thing you must do is stop your camera from doing things like automatic gain. But see how the high becomes almost skeleton-like, and that can be much more convenient for classifying the characters if you're doing that as a next step for your algorithm. And what we've got is median filter, which looks like a blur. You can see this one, the frame rate chugs on this, but it's a much more intelligent blur, as it were. It's amazing how median filter actually works and gives you anything useful, but it removes basically what's called salt and pepper noise. So this, if let's say you're transmitting your image over a old bit of cable or something, and you lose a few bits and a few bytes here and there, this kind of algorithm can reconstruct it. We're artificially using a large median filter kernel here. It's 5x5 instead of 3x3, so that's why we're sucking performance. And finally, adaptive threshold with usable components. Is it worth talking about setting the number of iterations? It probably is. I probably should add that just for completeness. Why not? If we're going to do it right, do it right. And as you can see now, we're slowly losing lots of code, which is quite nice. Yeah, I said it would be under 500 lines by the end of it. I don't include the things at the top. I'll get rid of that now as well. And I'll probably start going through and tidying up some of these things. See, the initialized webcam to console dimensions is not anymore, it's to screen dimensions. We just cut and paste that from the console game engine. We've got a selection of algorithms to choose from. I'm just so it looks nicer on GitHub, really. Morphological operations, fine. So which ones of these are we not using? We are using activity, I think we are actually using all of them. Primer, let's put a little flag. Do we even need the priming circuit anymore? I don't think we even need it. Let's just try it without. So the priming circuit was used as part of the temporal filtering algorithm because it took, for some reason, a long time for the image to come up to speed. And it was just to make it a little bit more visually pleasing, but I just don't think it's necessary anymore. There we go. Let's just try it without the priming circuit and see what happens. So this was for low pass temporal filter. Yeah, you see, I think it's fine. I don't think we need it anymore because there's always data in there anyway. If the application started up from nothing and somebody went to low pass temporal filter, the output register's already got sufficient simple data. So that's a complexity I can do without. Why do I need to explain to somebody why we need to prime that just to make this video? And that's quite a bit of a tricky thing that I often am faced with. I want things to be fun and easy to use, and also at the same time very explainable and visible to the user who looks at the code. But if I throw in something like a priming circuit, they have to then try and understand why does it need a priming circuit. And that's a little bit perhaps out of scope, because they need a priming circuit because of how I've got this set up. It's not really that relevant. So I've got my algorithms, done all those. So we wanted to now set one last thing, which was the number of iterations required. Do I have any of these that do anything with an integer value? No, not yet. So that's what we'll just pinch those and add it to the morphological one. So this is going to be 395 and 405. I think we're getting quite close to the bottom of the screen. Change iterations with, we're using the Z and X keys already, so that'll now be A and S keys. Above it, current iteration count equals standard, and what did we call it? I can't remember. Nmorph count. Okay. So we say A and S keys. Let's do a little bit of user input at the start of our morpho. I'm trying to pick something that looks similar to what we've already got. There we go. Take U and morpho. Respond to user input. A bit more user input on this one. A and S. So press the A key. We want to set our nmorph count value. We want to decrement it. Otherwise, we want to increase it. No need to modulate with f-elapsed time anymore because this is a finite number. It's nothing that happens in real time. And we do want to clamp these things because we need it to happen once. But we probably want it to happen less than 10 times. Things will start to get very slow. And I've made no attempt in any of this to actually optimize any of the image processing code, and that will probably get quite a lot of negative comments. You'll be surprised saying, "Oh, we should be using OpenCV," and you should. People miss the point. They don't seem to see that I'm trying to explain what is it that OpenCV is doing, not how does it do it. So I also want to clamp it at 1. We need at least 1 to occur. So that's between 10 and 1. And our threshold here for all of these is now nmorph count. Nmorph count. Nmorph count. And that one, you know what? That one's probably totally useless. There's probably no reason at all to be doing that one multiple times. And I'm reasonably convinced of that. So let's just take out that complexity. Right, let's take a look. Play. Right, so what we're up to is morphological operations, output Z, X, and edge. Yeah, so you don't need it to do it multiple times for edge. But for output, so if I now press S, I don't want to use be held because it's too fast. Okay, we go to the other way. We're expanding the image outwards. So let's take, for example, what if you wanted to isolate this portion of the screen with all of these buttons on? That could be quite tricky, but by dilating a few times, you can sort of glob things together. And then once you've globbed it together, you can erode a few times to get rid of all of the stuff that's there, except for the main blob that you've found in the middle. So it's really a spatial grouping algorithm. I'll perhaps need to think of a sensible test piece for that. Let's have a look. So this one is getting rid of the high, for example. Pressing the wrong buttons there. So this is a dilation. This is a single dilation, but within 2 dilations I've removed the text from this blob. Now I could then do 2 erosions to get the image back to its more or less how the original image looked, more or less. But there's no information to ever reconstruct that high, so it's effectively I've removed it from the image just by some simple image processing. And I'll have to have a think about how to describe that in the video. But I don't want that on be held, I want that on be released. So you actually have to press the button. So I can take that out. I'm still a little unsure why I need this activity register, but no, actually I know why I need it. Yes, because we need to change everything in a sort of homogeneous way. Median filter, fine. Respond to keyboard input, fine. Done all that. The only thing we've not got it doing is displaying the current algorithm. So that's the kind of thing I might add in after I've made the video and before I put it on the GitHub. And so I think, in terms of being prepared for a video demonstration tomorrow, writing a bit. So the plan is I'll go through each of the bits. Bit 1, threshold. But I'll show then the effect using this tool that I've created, and then I'll talk a little bit on OneNote slides about what a threshold is doing. And then I'll probably just talk through the code. I won't type it all out bit by bit, because I really want it to be focused on the image processing. JavaX9. So it doesn't go ping even if you at me. Sorry about that. So I don't know if you've got things, messages, so sorry if I've missed them. I think you did before, but teaches all how to operate overload. No, I did specifically, yes, a video on operator overloading. Let me just pull up the channel. It was quite a nice, I thought it was quite a nice video. It was certainly well received, much better than I thought it was going to be. And I create, your standard, it's the standard thing. I create a vector class and show how to implement the operator overloads on it. In fact, I can show you. I don't need to show you the video because it's now included in the Pixel game engine. There it is. So here we took this is what the video was about. It was about creating just this class. It introduces both templates and operator overloading to create a reasonably flexible 2D vector class, which then the Pixel game engine goes on to use. Right, so let's just have one last look at the algorithm. I think we've got all of the 8 bits. There's a lot of descriptive text at the bottom, but it's nice and simple. What do you guys think? I mean, this is an opportunity to have some input into the output of a video before it goes out. I think it's a nice tool that somebody can download and learn. The one limitation I'm really consciously aware of is I have no Linux alternative for camera input. So if anybody that knows anything about Linux can have a think about that, certainly let me know and we can probably do some sort of PR on the GitHub. None of this is on the GitHub just yet, of course, but that's the first thing I'm going to get asked is, how do I do this on Linux? Sibel HDText, that's number 4. Oh no, number 5 is Sibel. I quite like the artificial bump map generator. It would be nice to include that, maybe as a little bonus extra. This is how the videos end up being 40 minutes long. You think, oh, what else am I going to include? Do you need a specific type of camera? I am just using a webcam. I've said in a previous video in this series, if you ever see on eBay or anything like that a PlayStation 3 DualShock camera, get it. They're fantastic cameras for home image processing because they can do 320 by 240, which is this resolution, in colour at 170 frames per second quite easily. And so this plugin, you have to download a driver, and the driver's a bit naff because it pops a little advert up in the corner when you want to use it. But as I used it throughout my research and PhD, I even use it in my work now where we've needed to do some slow motion records or we've needed incredibly high frame rates for things. They're just a very versatile camera, and even though the driver pops an ad up, the driver itself is really simple to use. And allows you to access all of the low-level hardware functions of the DualShock 3. So it can do things like spherical aberration correction and spherical distortion in hardware combined with the driver before it comes back. Because, of course, don't forget the PlayStation camera was used to detect the motion controllers, amongst other things. So it's actually primed for doing image processing with, whereas a webcam is primed towards capturing pretty pictures of good-looking programmers to broadcast all over the world. I think it's a similar thing. The PS2 iToy it's more than just a webcam, Can you turn the background into a gradient color? Yeah, probably. But it would be quite a costly operation to do it each time. The easiest thing would be to prime a gradient in the background as a sprite and then just draw that gradient to the screen rather than having to calculate it. I guess it makes no difference. A diagonal gradient would be a little trickier than, say, a vertical gradient. But I don't think I want a gradient in the background. So what would we have as a thumbnail? Probably... See, these sort of things make nice thumbnails. That one probably doesn't. That one probably doesn't. People will respond to that. So it's got to be something you can kind of look at and see straight away what's going on. Perhaps the binary morphological edge. Yeah, maybe if you found the right scene for that. Something like that. I don't know. I'll have to have a think. I usually only choose the thumbnail as part of the video editing sequence. As my first sentence was too far to cut and paste it, take this link. I can't see what the link is. I just three little stars. Right, so the next phase of the project, because the stream is going to end now. Tezza, if you're streaming, shout out. But what the next part will be is tomorrow I'm going to record the video, and I'm actually going to live stream the process of me recording the video. Now, it won't be very interesting or interactive, I'm sure, but I just wanted to complete the set of streams that I'm doing, because whilst I'm making the video, my intention is to set up a laptop and use the laptop camera to just capture all of this whilst I'm doing the voiceover work and whilst I'm writing the code and whilst I'm doing the screen stuff. And whilst I'm doing that, I won't be interacting with the chat, simply because that's time to focus at that moment. Because making a video, it's not. For me, I enjoy it, but it is sort of the less enjoyable part of the project, and I just really want to power on through it. I'll make mistakes and I'll make errors and I'll have to rethink about what I want to say, and there'll be awkward pauses and silences. So it'll be more just a camera looking at it, so I've captured it and it completes the series that I'm personally trying to create. And then hopefully once I've done the filming, which I'm expecting will probably take somewhere about 2 to 2.5 hours, then I'll take a little break, and maybe on Sunday I'll do the editing. Again, I'll try and live stream the editing. That's a bit more interesting to show, but I don't know how well my computer's going to be able to handle doing live video editing and live encryption of the visible screen and transmission to the internet all at the same time. I'm also undecided yet whether to do a 2-camera video or not. So those familiar with my channel will know that some of my videos I look to the camera and say sarcastic things and do introductions, and others I don't. And typically for something like this, I probably wouldn't. If it's about a specific algorithm, I don't really want to confuse it by cutting to the camera all the time. There's a bit of an artistic thing in there. But also, if you're ever wondering why I don't do all of my videos to camera, I just can't be asked. You know, I don't want to have to brush my hair. I don't want to have to put a nice clean T-shirt on or anything like that. I'm a human being. I just want to get the information out to the user. So that's really the truth behind that. Oh, hey Tessa, thank you very much. Thanks for listening. Sorry for being annoying. You're not annoying at all. That's exactly what these streams are about. People are allowed to shout out and have conversations and all sorts of things. It's not a problem. I like interacting with my audience. I know if you've come over from the YouTube channel, and I always say this in every video now, and you're wondering why is it not like the YouTube channel, it's because this is the real life. This is what's going on behind it. This is the putting it together. And it's always great to see the community sort things out. So did you say you were streaming? You're not streaming, you're not. Okay, fair enough then. Well, with that, thank you very much everybody. It's been a long stream, this one, 2 hours, so thanks if you've stayed the course, and I will see you next time. I'm going to be on Discord though. So good night everybody, and let me click the button. Take care.